Why hello kids and welcome! So I'm going to teach you guys about the second right hand rule. So the first one we got was from, you had a current, right? You had a current that was moving in a wire. Your thumb was the direction of the current. Your fingers curled in the direction of the magnetic field. So thumb went this way, fingers curled, and there you go, you got the direction of that magnetic field. This is now going to be, how do we determine the direction of the magnetic force if I know an external magnetic field and how fast the velocity, or the direction of the velocity or the current of the moving charge? And what do I do if the charge is negative as opposed to the charge being positive? So we're going to start with the positive charge, and we're going to use our right-hand rule. So this I call right-hand rule 1. That's where I can find the magnetic field due to a moving charge, or vice versa. This one's going to be right-hand rule 2. Right-hand rule 2, you do like this. Right-hand rule 1 is like you curl like that. Right-hand rule 2 is like this. So the way it works is that your thumb is still the direction of the current. Your thumb is still the direction of the current. Your fingers are still the direction of the magnetic field. The only difference here is that your palm stays like this, and you imagine that out of your palm is a vector arrow pointing this way. Give me a second. Here you go. Like this. Right? There's a vector arrow pointing out this way, and the tip of this arrow, we say, so the vector is pointing out that way. And this is the magnetic force, this imaginary vector that goes out of your palm. So again, current, magnetic field, force. So the force goes out like that. Okay, so let's see if we can do this using our newfangled right-hand rule. And we're going to do it by, hopefully you can see the screen okay. So it basically says we got a magnetic field here. Magnetic field, they're X's. So the X's are the magnetic fields. That means it's going into the page. Remember, X's are into the page. And I got this positive charge here, and it's moving to the right. So I'm going to use the right-hand rule and try to determine what's the direction of the force. So let's see. My fingers are the current, so the current needs to be pointing to the right. So the velocity points to the right, like that. My fingers are the magnetic field. Those point into the page like this. And then lastly, my vector arrow would point up on my palm, so the force would point up. So what, we got the magnetic force, what is it going to be, this? Yeah, so the force would point up, FB. Alright, let's try another one. Oh, just a reminder to you, this is the way you can, hopefully you saw this video already, but to calculate a magnetic force, there should be a vector arrow right there. It's the charge multiplied by the velocity. It's the charge multiplied by the cross product of the velocity and the magnetic field vectors. That's why we got to use this right-hand rule, because we got a cross product going on. So the velocity cross B, there you go. Once again, V cross B, that's just Q, V, B, the magnitudes, times sine of theta, where theta is the angle between the velocity vector and the magnetic field vector. Alright, let's actually try another one. So here we go. We got the magnetic field now pointing to the right here. We got a moving positive charge going up. Alright, let's use our right-hand rule. Again, thumb is current. Fingers are magnetic field. Palm is force. See if you can predict it. And now let's try. So here we go. My thumb goes in the direction of the velocity like that. The magnetic field points to the right, so I got that good. That means the force is going. This one's fun because you get to slap it. I'm not going to slap my TV. I like my TV. Good TV. So, yeah, it's going to go into the page. So the force is into the page. How do I draw that? With an X, yo. There we go. Forces into the page. Next one. Uh-oh. Uh-oh. It's negative. There's a negative charge. Don't use your right hand. You don't use your right hand for a negative charge. If it's a negative charge, that's right. You use your left hand. Hi, Bella. Yes, I see you. You use your left hand. So if it's a negative charge, you just switch to the left hand. Everything else is the same. Velocity, magnetic field, and force. Very good. Good job. Good helping. All right. So I got my velocity vector points up. The magnetic field points to the right. So the force then has to point out of the page. Yeah, the force points out of the page. The force points out of the page here. And notice it was the same situation as the positive charge. It's just now a negative charge. And instead of going into the page, it goes out of the page. So some other methods, let's see, out of the page is a dot. So some other methods use, they say, use the right hand rule and then just do the opposite with the negative charge. I don't like that. I just say, just use your left hand. Just, yeah, okay. So next one we'll do is, okay, we got the magnetic field is pointing to the right, the velocity is pointing to the right, and we can use our right hand rule to find out what the direction is going to be, and here we go. So the velocity is going to the right, the magnetic field, uh-oh, I got an issue. I can't put both the magnetic field to the right and my velocity to the right. That's just not going to work. What the heck? How do I do this? How do I solve this? Oh, wait! That's right. Theta is the angle between the velocity vector and the magnetic field vector. The angle is 0. So the force must be 0. One more kind of trippy one. Whoop. Don't look at that. So here now we got another magnetic field pointing to the right, and we got a charge that's just at rest. We got a charge at rest. Well, if the charge is at rest, then there's no velocity. If there's no velocity, there's no force. No moving charge, it's not going to produce a magnetic field, so it's not going to interact with the external magnetic field. All right, so FB equals 0. Again. All right. So I have more, but I think I'm going to stop there so I'm not taking up too much time per video, and I hope that helped. See you later. Bye.